Given this question that says that we should find the mass of planet Earth whose radius is measured to be this particular value meters, we need to account for this particular example illustration image here which highlights Earth, and we have the following to highlight in this particular image of Earth, which is the following. We have a radius, and this radius here takes into account the following: the distance from the center of this particular central body to where any object is positioned around the surface of the Earth's surface. So in this case, if I have a specific object that is placed rightly on this surface, this object's distance from its center of mass to the Earth crust is highly insignificant. It is not actually significant because relative to the radius of the Earth, which is this particular orders of magnitude, is really huge number. So in conclusion, we can approximate the distance from the center of this particular object's mass to the center of the Earth to be pretty much the same as the radius of the Earth's surface. So therefore, if we're highlighting, we are going to go all the way from here to the center, which is represented as our radius of Earth to be equal to 6.38 times 10 to the 6 meters. And so now we're able to establish this. There are a couple of variables to take into consideration and parameters to analyze on this particular image. One is that, yes, the red dot here experiences a gravitational force that is going to be expressed as Fg, and this particular Fg is known to be called or is gotten from Newton's second law of motion, which is the net acceleration acting on an object. In this case here is the gravitational field force that is from this central body. That is what this red dot is experiencing. And while on the other hand, the two object relationships, which is the red dot and the central body, which in this case is Earth, is experiencing a law of universal gravitation, which is expressed as F huge G. This here must be equal to each other in order for we to be able to analyze the mass of the planet Earth with that particular radius. We know that this F small g is going to be equal to the mass of this small dot object multiplied by the gravitational field that is experienced by the red dot from the Earth's surface, which in this case the Earth's surface is expressed as the central body. And so this here is equal to Fg, which is huge G, to be equal to the big G, which represents our universal gravitational constant, and this here is multiplied by the mass of our central body, which in this case is Earth mass, and finally this is multiplied by red dot's mass. This here is all divided by, on the right side, the radius, which is r squared. R represents the distance between the center of one object to the center of the other object. Remember that we made this particular red dot to be negligible in terms of its center to where it is touching the Earth's crust. So therefore we are going to just account for our r to be equal to the radius of Earth. So that is the assumption to be made. Therefore, rearranging our g in here, which is the small g, means that, take note that on the left side and right side we have the mass of the red dot to cancel out. Therefore our red dot's mass is negligible in this process, and we have our g to be equal to the following: big G, which is a universal gravitational constant, multiplied by the mass of the central body, in this case is Earth, all divided by r squared. Remember that r g represents the gravitational field strength, and that is how much that red dot is experiencing from the central body, and that is how much the central body is producing on any object around its surface. So this here, when we are looking at this equation, we need to remember that yes, since the question is asking for the mass of planet Earth, we are going to solve for our ME, and therefore solving for our ME results in the following. ME is equal to small g multiplied by r radius squared, all divided by r big G. Now remember that where big G is equal to the universal gravitational constant, this is represented as a number and its unit, and remember that the number that you should remember is going to be equal to 6.67 times 10 to the negative 11 Newton dot meter squared, or divided by kilogram squared. And so this universal gravitational constant can be found usually at the back of the textbook or any other relevant resource that will be provided to you, and so that is something you should keep in mind. Another constant to remember based on this equation is G, which is the small g of Earth, which is, everyone knows it to be 9.8 Newton of force acting on a 1 kilogram object, or you can actually say this to be equal to 9.8 meter per second squared. Because of the purpose of our universal gravitational constant, we'll be using this in here rather than this meter per second squared. Finally, here is we need to take into account the r, which is in this case the radius of Earth, and this is equal to 6.38 times 10 to the power of 6 meters. And therefore what we are going to do is solve for our ME, where we know our ME to be expressed as this. We are going to put in our numbers in place of the variables, and this is how it looks like with the unit, where ME is equal to 9.8 Newton per kilogram. This is multiplied by 6.38 times 10 to the 6 all squared, multiplied by meter squared, all divided by 6.67 times 10 to the negative 11. This is multiplied by newtons point meter squared, all divided by kilogram squared. This point, remember, represents multiplication. That is something to remember. And so we are going to evaluate our units, and we notice that yes, our newtons cancels our unit. We have our meter squared cancelling out our meter squared. Remember that this kilogram squared is actually numerator overall, and this kilogram here is represented as denominator overall. Therefore, one of these kilograms is going to be cancelling out this kilogram, and what we are left with is kilogram at the numerator, which is the units that we want. And our final answer says that yes, the mass of Earth is equal to the value 5.98 times 10 to the 24 kilograms. And this in here is our final answer, and truly our approximately this number here is close to the actual value of the mass of Earth. And it's really wonderful to see how, looking at this question, we realize that there are a couple of things to keep in mind. We need to take into consideration and assumptions which includes that an object is actually really small, but not to the small atomically level sized, but rather something I would say physically looking sized. But yeah, it's on the earth crust, and its distance from its center to the earth crust is really significantly small. We are assuming that the r is pretty much the radius of earth. We also take into consideration that yes, the gravitational field force is equal to the universal gravitational law, and this here is going to be our expressions that led us to our mass of earth, and we are able to put in all these variables and values to determine the mass of earth, and this is how it is done. Thanks for following me through this. Truly appreciate it. Hit the comment down below. Let me hear your thoughts about this. By that way, I could talk to you all soon. Stay smart as always and believe in yourselves.